Hi, welcome to Computer Science Explained. In this video, we'll talk about implication, equivalence, and exclusive or logical operators. The implication operator is a binary operator. In other words, it needs two input arguments. False implies false is true. False implies true is true. True implies false is false. True implies true is true. Logical formula, not X or Y, gives us the same truth table. Not false or false equals true. Not false or true equals true. Not true or false equals false. Not true or true equals true. To memorize this truth table better, you can think of implication as an estimation of work. If left operand x is input and right operand y is output, only when we get true as input and make false as output, the result is false. So only when the input is better than the output, the result is false. In other words, the result is false only when we make work improperly. Now let's see the set theory interpretation of the implication operator. All except x united with y is true. Also, the implication operator can be emulated with the less than or equal operator. Let's check. 0 is less than or equal to 0 is true. 0 is less than or equal to 1 is true. 1 is less than or equal to 0 is false. 1 is less than or equal to 1 is true. X implies y can be interpreted as if x, then y. In this interpretation, the implication operator is also called the conditional operator. The left operand is antecedent, and the right operand is consequent. From this point of view, if x is true, then y also must be true. In the set theory diagram, this corresponds to the intersection of x and y. If x is not true, it doesn't matter whether y is true. In the set theory diagram, this corresponds to the complement of x. The equivalence or bidirectional implication operator is a binary operator. In other words, it needs two input arguments. False is equivalent to false is true. False is equivalent to true is false. True is equivalent to false is false. True is equivalent to true is true. The logical formula x implies y and y implies x gives us the same truth table. That is why the equivalence operator is also called bidirectional implication. False implies false equals true. False implies false equals true. True and true is true. False implies true equals true. True implies false equals false. True and false is false. True implies false equals false. False implies true equals true. False and true is false. True implies true equals true. True implies true equals true. True and true is true. Now let's see the set theory interpretation of the equivalence operator. X implies y intersected with y implies x is true. When both x and y are true, or both x and y are false, the result is true. In other words, the values of x and y must be the same. Thus, we can use the equality operator which gives us the same truth table. False equals false is true. False equals true is false. True equals false is false. True equals true is true. Also, we can see that x is less than or equal to y, and y is less than or equal to x gives us x is equal to y. The exclusive OR operator is a binary operator. In other words, it needs two input arguments. False XOR false is false. False XOR true is true. True XOR false is true. True XOR true is false. The logical formula x and not y, or y and not x, gives us the same truth table. False and not false is false. False and not false is false. False or false is false. False and not true is false. True and not false is true. False or true is true. True and not false is true. False and not true is false. True or false is true. True and not true is false. True and not true is false. False or false is false. Now let's see the set theory interpretation of the equivalence operator. As we can see, x and not y united with y and not x is true. So, in other words, when left and right operands have different values, the result is true. Also, if we subtract the intersection of x and y from the union of x and y, the result will be the same. Let's check this with the truth table. 0 or 0 equals 0. 0 and 0 equals 0. 0 minus 0 equals 0. 0 or 1 equals 1. 0 and 1 equals 0. 1 minus 0 equals 1. 1 or 0 equals 1. 1 and 0 equals 0. 1 minus 0 equals 1. 1 or 1 equals 1. 1 and 1 equals 1. 1 minus 1 equals 0. We can achieve the same result without using a minus operator, which is not a logical operator. This formula resembles the previous one. False or false is false. False and false is false. Not false is true. False and true is false. False or true is true. False and true is false. Not false is true. True and true is true. True or false is true. True and false is false. Not false is true. True and true is true. True or true is true. True and true is true. Not true is false. True and false is false. Let's see this formula in the set theory diagram. Exclusive OR can be emulated with not equal to operator. Let's check. False not equals false is false. False not equals true is true. True not equals false is true. True not equals true is false. As we can see, the results are the same. The equivalence operator is opposite to the exclusive OR operator. When the equivalence operator has true values, the exclusive OR has false values and vice versa. Of course, equal and not equal are opposite operators. The set of the equivalence operator is the complement of the exclusive OR operator and vice versa. Thanks for watching. See you next time.